Well, good morning, everyone. I want to welcome you to the first session of the Biostatistics for Biomedical Research course. I'm really glad you're here. We have a lot of things to cover over the coming months, and we'll be getting input from you for some of the topics that we'll be covering. My department at Vanderbilt University is the Department of Biostatistics. I'm a professor of biostatistics in that department. And this course is sponsored by the Department of Biostatistics. And our university is in Nashville, Tennessee, United States. And the course is also sponsored by the Vanderbilt Institute for Clinical and Translational Research, its Research Methods program. And it's also supported by the Edge for Scholars program at Vanderbilt that is led by Kathy Hartman. We're very fortunate to have three moderators here today. We have Tom Stewart from my department at Vanderbilt, and also Matt Shotwell from our department, and Donald Slozak is here from IDEX Corporation. So they'll be monitoring the chat line and helping with questions. You'll see in the YouTube live chat these three dots. The live chat is usually at the right of your screen when you're on your browser to this streaming video. And if you see three dots here, if you want to pop out the chat to another window, which you don't really need to. But you'll also see where it says top chat. You really want to modify that to live chat, because that will make the most recent messages come out next, instead of trying to sort them by popularity or something like that. So I would suggest that you convert that to live chat. Now, I've had a lot of experience teaching biostatistics, especially to clinical investigators. I've never put on a YouTube live streaming event before, so I hope you'll bear with me. This is pretty new. And the thing that I'm least familiar with is how to handle questions and answers. We have hundreds of people logged on, and many of you will want to answer questions, and it's impossible to get to all the questions. So I hope you'll use the chat wisely, especially for short questions. Use it for questions that have not been asked already. But I will not be watching the chat very often as we go. I'll stop occasionally to look at the chat. And the moderators will be analyzing what you write and posting for me some questions for me to address. And so there'll be a delay in responding to your questions, so please keep that in mind. Also, for questions that are long or involved, or questions that you think of after the hour is over, you can post those on datamethods.org, where we have a topic set up. So if we were to look at the main web page for the course, you see towards the middle part of this page, you'll see some to-dos. So to-dos before the session, which hopefully you've already done, and things to do during the session, especially how to deal with questions, and things to do after. And those of you who are watching this by recording later will be using only the datamethods.org for asking their questions. There's some recommended reading that I strongly recommend, and then there's some important links, including the course notes, a discussion board about general issues about the design of the course and possible future topics to cover. There's a hashtag to use in Twitter communications, a glossary of non-statistical terms, a glossary of statistical terms for non-statisticians, I should say, some nice background material, material on statistical graphics and other topics, and there's some analysis of you as a population of course participants that also exemplifies some of the statistical graphics things that we'll be talking about. So keep track of this website because it'll help you stay up with what's going on in the course, and you'll click on the session schedule to find out what specific topics will be covered and what are the dates of the different sessions. And so if I can move my cursor up a little bit, we see a link here to the course schedule. And you'll notice in the second session, which is for a week from now, there is a pre-session assignment. So take a look at that. And each session has its own offline discussion link that's pointing to a special topic for that section in data methods. So we're going to get right into the course and start looking at the notes for the sections for today. This is a section on general overview of biostatistics. So there's some nice quotes for your enjoyment there. And then there's a section about what is biostatistics. So statistics applied to biomedical problems is biostatistics. Decision making in the face of uncertainty or variability, that's shared with general statistics and biostatistics. Design and analysis of experiments, doing detective work in observational studies, such as in epidemiology and outcomes research. Attempting to remove bias or find alternative explanations to those posited by researchers with vested interest. Statisticians sort of pride themselves as being the Sherlock Holmes of science. We do a lot with experimental design, refining measurements, descriptive statistics, graphics, analysis, inference, and prediction. And a key necessity for biostatistics is that it be integrated with the subject matter. And so biostatistics is not something that you sort of come to somebody at a window and say, I need a statistical test. It's really part of team science, and it needs to be run as team science, or it really will not be successful. It will not meet the needs of the team, and the team will not understand our concepts. We also have to recognize that, and the team has to recognize that experimental design and execution of studies are all important. So the next section is an all too brief introduction to the three main branches or schools of statistics. These branches are not quite as distinct as this makes them sound, but it's still a helpful categorization. And so the most commonly invoked branch of statistics is the frequentist school, which is traditional statistics. And then there's Bayesian statistics, which ironically is much older than the frequentist school, but it didn't really start to catch on until the computational tools started becoming available that make it feasible about 20 years ago. And then there's the likelihoodist school, which is a bit like Bayesian inference, but without the priors. That's an oversimplification of it. When we get later into section 5.3, we'll get into these schools in much more detail, and you'll know what they offer. Now, statistics has fundamental principles, and these are the ones that I've compiled into a list over the years, and I'm sure I'm forgetting something very important. But I really believe in these principles, and when you don't hold to the principles, things tend to go wrong. And statisticians who are practicing in the field and working with a lot of collaborators, they need to have their own principles because, for example, if somebody asks you to do something that you don't think is good science or you think it's actually wrong, such as engaging in p-hacking, you need to know what principles really don't allow that to happen so you can stand firm. And so one principle is to use methods that work, and there's two ways to show things will work. There's theory and there's extensive and realistic simulation. You have to understand uncertainty, design experiments to maximize information and understand all the main sources of variability, use all information and data during the analysis, and use discovery and estimation procedures not likely to claim that noise is signal. So this has to do with fishing expeditions or exploratory analysis, p-hacking, and so on. Strive for optimum quantification of evidence about effects. So that's one of the most important things that we do in statistics. And then the next point is going to be a lot more difficult to understand, and we'll be elaborating on that in a later section, in another session. Give decision makers the input they need in order to take action or make decisions. So the decision makers, they know the consequences of the decision, and that's up to them to specify the consequences, which goes into what's called a utility function, also called a loss or cost function. That's something the analyst does not have control of, nor should she. But we need to give the decision maker the inputs that they need to make the best decisions. And so we generally feel bad about giving inputs to the decision maker that are not directly actionable. So if you give somebody probabilities that condition on the unknown or condition on the future, those are not in the predictive mode. And so they're conditioning in the wrong order of information flow. So good examples of that are in medical diagnosis. Sensitivity and specificity are in a backwards information flow order. So they are the probability of the test result given the disease status, and the disease status is what you're trying to determine. And once a test is known to be positive, the probability that it would be positive if you have disease is completely irrelevant. So you already know it's positive. There's no real probability associated with that. So that's a good way to start understanding that some probabilities are not actionable because they don't feed directly into decisions because they're in the wrong information flow or time order. P-values are like specificity in the diagnostic realm. So p-values condition on an effect being zero, so they can't tell you any information about the likelihood the effect is being zero because you've already assumed that it is. So that is analogous to specificity. Then we need to present information that in ways that are intuitive, maximize the information content, and give the correct perception. And giving the correct perception is a main goal of modern statistical graphics. So what can statistics do for you? Well, this is a list I'm going to go through fairly quickly, but refining measurements is one of the most important things statistics does that people don't pay enough attention to. And we'll talk more about that. Experimental design, everybody knows that's important until somebody gets in a hurry and they throw a machine learning algorithm on a bunch of data, and experimental design seems to sort of go out the window all too often. So you need to make sure that the design answers the right question, takes into account sources of variability, sources of bias, and then often a good design is one that's sequential or adaptive. It takes a lot more thought, and then the design should not waste any subject. So when you get a subject in the data, you want to make full use of that subject in your effective sample size. And then in strong collaboration with epidemiologists, statisticians are involved in observational study design. In strong collaboration with epidemiologists and philosophers, they're involved in causal inference, which is a very difficult field and very philosophical. And then we want to use methods that preserve all the information in the data, to use robust analysis methods. We want to estimate magnitudes of effects. And then a real important thing that we do that's not discussed very often and is often the most interesting result is to estimate the shape of an effect of a predictor. So you might not have a linear effect, and whether that goes up quickly and then it tails off is something that's very interesting to the subject matter experts. And so estimating shapes is very important. Quantifying causal evidence for effects if the design is appropriate. Adjusting for confounders, modeling effect modification or interaction or heterogeneity of treatment effect, those are all really the same thing. Developing and validating predictive models, choosing optimum measures of predictive accuracy. These are all important things quantifying information added by new measurements, handling missing data or data measurements below a detection limit. Provider profiling is a big application of statistics. So how do you compare hospitals? How do you compare surgeons, health systems to do risk-adjusted scorecarding? Visual presentation of results, taking into account graphical perception, finding alternate explanations for observed phenomenon, and fostering reproducible research. There's a link here you can look at later that has more detailed benefits of biostatistics, especially for more basic research. So now we get into statistical scientific method. Statistics is not just a toolbox. That's a common misconception, and it's not just a bunch of formulas. The things that statistics does, the most important things really don't involve a whole lot of math. But it's a way of thinking, and it's a way of designing studies. It's an evidence-based way of thinking. And so, in understanding the problem is key to a successful analysis. So you have to frame the question properly to address it. You have to understand and optimize the measurements, understand sources of variability, and much more. So there is a really nice paradigm developed by McKay and Oldford, and I learned about this from David Spiegelhalter in his wonderful The Art of Statistics book that came out this year. And they have this 5-stage system: problem, plan, data, analysis, and conclusion, PPDAC. And I think this is really important to think about when you first start a collaboration, and to make sure that you get in on the right stage of the collaboration. There's several collaborations that I've been involved in where the data have already been collected, and I really had to disengage from that because the input I was mainly giving was going to be too late. So these are the 5 elements of their system. Problem, you talk about process measures and units of experimentation and target population. Response variables, all important. Explanatory variables and other things. What are the aspects of the problem? Causative, descriptive, or predictive? And then there is planning with regard to various features such as the population and what measurements to make on units in the population. Selecting the response variable is another. It's also important in this aspect. Dealing with explanatory variables, the sampling process, the measurement process, and so on. And then there's executing the protocol or the experimental design, recording departures from that. It's incredible nowadays how many studies get done where there was no plan. And it's unfortunately the case that a good deal of research using electronic health records falls into this category. So you really need a plan to guide the project and to teach you when you have the right variables measured and the right patient or subject subset. Monitoring the quality and completeness of data, consistency, storage, annotating data, and all those things. Then there's all the analytical issues that we hear of more often, including formal analysis. And then there's the conclusion where you synthesize the results and present the results effectively and understand the limitations and potential errors. So that's a really great paper that really helps you organize the big picture planning for a study. And then we have types of data analysis and inference that was touched on a minute ago. So there is a goal of description, and that's just telling what happened in the past. You're not trying to predict the future or to infer to something bigger. You're not trying to generalize. Then there's inference from the specific to a general, so you might infer something by analyzing data from a sample, and you're trying to make a generalization to the population from which that sample of people came. And as part of that, there's hypothesis testing and estimation. So with hypothesis testing, we might test a hypothesis about population or long-run effects. We sort of use those two things interchangeably. And then estimation, we're estimating a population or long-term average quantity. Now, when you get to Bayesian inference, things are a little bit different. So with Bayesian inference, the data may not be a sample from the population. It may even be impossible to ever replicate this study, observational or experimental study. May be impossible to obtain another sample from the same population. So what does Bayes do? Well, it's really got a very different philosophy. With Bayes, you seek knowledge of the hidden process generating this particular sample. And this sample can be a one-time sample. It could be a particular political event, like a particular election that will never be held again. It could be a particular war that hopefully never happens again. And so by trying to discover what is hidden, the data do not reveal the process used to generate themselves. This is the goal of Bayes. So whatever is generating the data, we would like to uncover it. We'd like to reveal it. And that's really a generalization of the concept of inferring to a population. And then there is prediction, predicting responses of other subjects like the subjects we had in our data based on analysis of patterns of responses in our subjects or patients. So we spend a lot of time doing prediction. Now, Leek and Ping had a wonderful short article, and they have this flowchart that I copied and pasted. Data analysis flowchart's really wonderful. If you're not summarizing the data, you're not really doing any kind of an analysis. Are you interpreting anything? If you're not interpreting anything, you're doing more descriptive. That goes in this category. Do you quantify whether your discoveries are likely to hold in a new sample? If not, then it's purely exploratory. And then are you trying to make predictions or are you trying to make an inference? And then there's a dichotomy between causal and mechanistic findings. So we're not going to be talking about mechanistic very much. But we'll be talking about inference and prediction and description and exploratory data analysis. This is a nice summary that they provided in their paper for what sort of errors are typically made when you don't match the analysis to the question that needs to be answered. So if you're doing an inferential analysis that you think is answering a causal question, then you have the classic, you may have the classic correlation does not imply causation problem. If you're doing if you think you're doing an inferential analysis but you're attacking it in a highly exploratory way, that's what's called data dredging, data mining, fishing expedition. And then if you are exploring and you really want prediction, you might make the error of overfitting. You're sort of over-exploring or over-interpreting the data, and that results in overfitting. And then you might be having a question of descriptive, and you're perceiving it as a question of inference, and it might be an N of one analysis that's really going on. So I would encourage you to read their short paper. I think it's very excellent. I'm going to stop a moment and see just what sort of questions we're getting. I noticed our moderators are active, which I really like that. So they'll be able to answer a lot of your questions as we go to make this as useful to you as we can. When I show the discussion board like this, I see the questions appearing in real time, but the streaming is about a 30-second delay. So when you see this particular screen, the discussion board will be about 30 seconds old, but I don't think that will matter very much. So I see some good discussion there, and thanks to the moderators for keeping things going and giving some great answers to some questions. And so I hope you all that have questions will continue to ask them there. And then if certain questions come up more than 2 times or 3 times, I think the moderators will give me a message to talk about those particular questions more. So now we return to the notes, and we're talking about types of measurements by their role in the study. Some of this will be pretty obvious, some of it may not be, but I tend to use the word response variable fairly general. Most people would say dependent variable, and response is just quicker. So response variable might be in a patient study, might be a clinical endpoint. It might be a final lab value. You might be monitoring kidney function, and you might have serum creatinine or GFR as an outcome variable, and it's a final measurement at, say, 1 year after a drug started. Then you have independent variables, which I tend to call predictors, even though I might not be doing prediction at the time. It's just sort of a convenient descriptor, and descriptive variable is another term. So an independent variable is something measured when somebody begins to be studied, and that's measured before the response is ascertained. The independent variables are often not controllable by the investigator. Sometimes they're controlled by how you enroll subjects. So you might do a study of only females, so you've taken total control of the sex variable as an independent variable. Then there are adjustment variables. Adjustment variable is a variable that's not of major interest, but you need to account for it because it may explain the apparent effect of a variable that you really are interested in. And it may also describe heterogeneity or in the severity of risk factors across patients. One of the most important aspects of confounding is called confounding by indication. So when patients get a certain drug because they're sick, the drug may actually look like it's making patients do worse, but it's just because you're selecting the sick patients to get that drug. So that's a very important type of confounding by indication. Then there's the experimental variables, such as the treatment that you randomize somebody to, the dose you may have randomized to. The experimental variable is an independent variable that is under the control of the researcher. So this table just gives some of the common terminology that we've talked about already. And now we talk about proper response variables, and the word proper is sort of loaded, and it's really intended to be loaded because this is one of the biggest problems we see in research. It's a big issue in drug development and really most fields where the dependent variable is concocted in a way that was say clinical researchers were trying to make it interpretable, but by trying to make it interpretable, such as giving a simple yes or no answer, did the patient respond to a drug favorably, it actually has many different hidden problems. So the response variable, which we'll always call capital Y, it may be a categorization or a dichotomization of an underlying continuous response variable. And the cut point that's used to make that dichotomization, I've never seen a single example where that cut point was actually consistent with data. So it was always arbitrary. It was often a statistical cut point, such as cutting at the median, which has absolutely nothing to do with biology. And these cut points have a lot of problems. We'll be getting to this in detail in a future session. There's a whole chapter in the notes called information loss that cover these sort of issues. So cut points have problems. They're arbitrary. They cause a huge loss of statistical information and power. Another problematic response variable is change. And change scores cause an amazing amount of problems in research, and I would go so far as to say that if you're calculating change and it's not a crossover study, you probably are doing something wrong. So change is a very loaded variable, and what's most important in most situations, say when you're not doing a crossover study, is the subject's most recent condition, not so much how the subject got there. So change scores hide important information, and they make you de-emphasize the last measurement in an inappropriate way. So what is a proper response variable? If you don't like the word proper, you could say non-arbitrary efficient response variable. So that's one that captures the underlying structure or process. It has low measurement error. It has the highest possible resolution. So if the underlying process is continuous, the measurement that you make needs to be continuous. If you're making a measurement that's continuous but it's got noise in it, such as measuring blood pressure using a cuff device, well, you might need to measure blood pressure 10 times and average it. That might be your response variable. Or you have a machine that automatically measures blood pressure every 5 minutes over several hours and averages that. That's a way to tremendously increase the precision, and that has a direct payoff in statistical power. If your underlying measurements are ordinal, you want an ordinal variable that has lots of categories, and you want to use a binary variable only if the underlying process is truly all or nothing. And this is probably the single biggest mistake that researchers make that matters. And there's a lot of talk about adaptive designs and modernizing how we do clinical trials. Nothing would have the impact of like improving the response variable to make it pertinent and have high resolution. Nothing could have the same impact in terms of learning and efficiency, lowering the sample size. We see a lot of response variables that are not proper responses because the response variable can be shown to mean a different thing for different subjects. So it has its ultimate impact, such as having some response to depression therapy. How that response predicts the ultimate success of the patient can be shown to be dependent on the baseline state the patient was in if you calculated a change score that should not have been a simple change score. So you want to have a response variable so that higher values are always good or always bad. But if the change score or the other measure you've calculated is inappropriately derived, this will not be true. You'll have some responses that are, for certain types of subjects, actually can be good, whereas for most subjects they're bad. So then we get into types of measurements according to coding. A binary outcome, like dead or alive, is frequently thought of as an all or nothing outcome, and that's not really the case. You can even do better there because how long you waited to die would be an important thing, and then how close you came to dying would be important. So someone who has a cardiac resuscitation and almost died, well, the fact they needed to be resuscitated is a pretty important thing to know, and those patients are ultimately going to do worse than someone who lived but never needed a resuscitation. So even in some simple cases, it's not as simple as all or nothing. But there are occasional situations where you see this. Then there's categorical, when there's more than two variables, two values that are not necessarily in any special order. So those are called, really these are meaning almost the same thing: nominal, polytomous, discrete, multinomial. And then there's ordinal variables. So that can be a categorical variable whose possible values are in a special order, such as by severity of symptom or disease, but where you don't assume that the spacing between the categories means anything. So an ordinal variable could be coded as A, B, C, D, E. Ordinal variables that are not continuous, they often have heavy ties at one or more of the values. And this creates a very strange distribution that makes you unable to use ordinary statistical methods. But instead, you need to use ordinal response methods. This happens when you're doing patient-reported outcomes and you have a floor or ceiling effect. You may have a lot of patients at the lowest or at the highest value of a certain scale, for example. So we need to handle ties and strange distributions. And we need to note that continuous variables are also ordinal, but ordinal variables may or may not be continuous. Then there's count data, where you don't have an upper limit, like the number of emergency room visits or number of traffic accidents in a month. So we use things like Poisson distribution for those. And then there's truly continuous variables, where you have lots of possible values. The continuous variables have the most statistical information, assuming that you use the raw values in the analysis. And continuous variables are usually the easiest one to standardize across hospitals or health systems or countries. Turning continuous variables into categories is arbitrary and requires a lot bigger sample size to have the same statistical information. And then in a later section, we'll talk about this interesting thing. This is a very common misconception, that if you have an error-prone measurement, let's say sloppily measured blood pressure, that if you categorize it some way into, say, 3 intervals, that somehow that helps with the measurement error. And nothing could be further from the truth, because if you have noisy data, you end up putting a lot of subjects in the wrong categories because you're categorizing on the basis of the noise, and you're actually making things worse. The one exception where categorization can help is if you're trying to get a voluntary response from a subject, and they won't give you an exact value such as their actual income, but they'll give you the answer to a 5 or 10 interval question about income categories. So if it induces them to respond, and you would otherwise not get data for that question, then categorization can be useful. There's some really good questions coming in that the moderators have pointed out, and so I want to stop for a couple of minutes and address some of those. So one of the questions is about why people are moving more towards Bayes, and that's something that we'll talk about a lot more in a future section. But I think the one of the reasons is the flexibility you get from Bayes. Another is we talked about the need to have actionable measures of evidence. So Bayes gives you actionable measures of evidence because it gives you, say, the probability that the drug works, not the probability of getting good-looking data if the drug doesn't work. So that's actionability. And then the ability to use outside information that's not from the current study. So an ideal situation for that would be you're trying to see whether a drug works in children, and you could enroll hundreds and hundreds of adults because there's so many more sick adults than there are sick kids. And you can't enroll near as many children, but you would like to borrow information from the adults to make an inference about the children for that drug. And we might borrow that information in such a way where Bayes explicitly specifies the probability that the adult disease process and the metabolism and pharmacokinetics of the drug are applicable to kids, and that probability won't be 0 or 1. So that goes into how much information you're borrowing. So that's just to give you a little preview. And then somebody asked the question, I hoped somebody would ask too, change from baseline is a common endpoint in drug development. How can this be improved? Well, this is one of my biggest battles in working with FDA, because the statisticians at FDA are truly incredible and smart and well trained, but they love to be helpful, and just like statisticians in academic medical centers and pharmaceutical companies, They want to be seen as helpful, and if they're seen as argumentative, sometimes they feel bad. It's never held me back through my career. And so we don't speak up enough. And when you really analyze what assumptions the change scores make, it's kind of incredible that they were ever used, and they're just used all over the place. So we have a section coming up where the assumptions of change scores are laid out in great detail to give you ammunition, and we really, really have to fight this. A very simple way to say it is the change score assumes that the slope of the pre on the post value is 1. And when it's not 1, you're going to lose power by using a change score. And then someone asks, would you say that studies are too often thought to be inferential when in fact they're exploratory? Should we do less hypothesis testing and more data description? I would say we should do less hypothesis testing and more estimation as well as data description. And I think that it is the case that studies are labeled as influential, and even going further, they're labeled as causal when they're not really using a causal design. And so I think it's a big problem, and you need to go back to the chart that I showed so you can properly know what it is you're able to do and not overreach. So we'll talk more about that later, but these are terrific questions. So let me bring up the notes again. So we need to choose the response variable to maximize statistical information, power, and interpretability. So you want your outcome to be a high information measurement. So study design is all important, and we're not really doing enough justice to study design in this course. We'll touch on it, but what you can do something about that makes an amazing amount of difference is following this advice here. The information provided by an analysis and statistical power and precision are strongly influenced by characteristics of Y. So if you have noisy Y, that increases the variance. It hurts your ability to estimate the effect of interest. That effect will be underestimated. If you have low information content, the power suffers. The minimum information response that you can measure is a binary outcome, and we'll say more about that now. So what would be the alternative? Let's say you had a maximum information outcome. It would be maximum information if you measured it multiple times and averaged it, but let's suppose you just measured it once and you have the typical sort of error. Let's say you're measuring systolic blood pressure. Well, I supposed here that you averaged over 5 readings to cut out some of the volatility. How much information is that? Well, we'll get to that in a moment compared to a binary. And then an intermediate outcome would be an ordinal outcome with a few well-populated levels. So there is a blog article on my blog, fharold.com, that really goes into this, and I'm going to show you just a few aspects of that blog article. When I pull it up here. Information gained from using ordinal instead of binary outcomes. So I think this will help you understand what sort of configurations you need to optimize the power. And the way this particular analysis does it, instead of seeing how the power changes, it just takes the other approach of seeing can you detect a less impressive treatment effect if you have a better response variable. So that goes hand in hand with power. But let's suppose we have a binary outcome and we want to detect a pretty massive effect, which is an odds ratio of 0.5. What's the sample size needed to do that? Well, it's 347 subjects in each of 2 groups. That will give you a power of 0.9. So that's your likelihood of asserting that there is a difference. if the true difference is this large. So what if instead of a binary outcome we had an ordinal outcome? Well, if you have an ordinal outcome that doesn't have too many ties in it, we're really talking about the Wilcoxon-Mann-Whitney two-sample test, which we'll cover later in the course. So if you were to use the Wilcoxon test instead of a binary outcome, what sort of power would you have? And then what happens with everything in the middle? So there's an R function in my HMIS package that makes these calculations really easy to do, and it tells you what the efficiency of a certain design is compared to the efficiency of a fully continuous response variable. That's efficiency in the sense of like ratios of variances sort of efficiency. So this table here I think is pretty intuitive for telling you what sort of information content there is in various configurations. So this is what we started with. You have 20% of the patients are going to die and 80% are going to live, if that's your outcome variable. Your detectable odds ratio from that configuration of your response variable, this is just your histogram with a distribution, is 0.5, as we said before. What if your outcome variable was evenly distributed, so it had an incidence of 0.5? You could detect a less impressive treatment effect. You could detect a 40% reduction in the odds of the outcome. What if you had 0.8 of the subjects at 0, 0.2 were at 1, and 0.2 were at 2? So we've got a 3-level ordinal, and you can see that since the 0.8 is dominating everything, your detectable odds ratio isn't much better than what we had from this situation. But what if you had it a little more distributed? So now we've got 0.7, 0.15, 0.15 of the population at these 3 ordinal levels. We can detect a less impressive odds ratio. What if you had even better distributed? Well, you can detect a less impressive effect. Or for the same effect, the power goes up. And of course, we'll be defining power in the future more. This is an even situation with 3 categories that's going to have a reasonable performance. This is a tilted setup with 4 categories. It's not going to be doing so well, but then when you have balance, you can detect a less important effect. And then you can see this carries on. So what you'd really like as your optimum is once you get to say 7 categories of Y, and they're all kind of equally frequent. So you have this uniform distribution that can detect an odds ratio of 0.64. If you were to do the Wilcoxon test without any grouping of the data at all, and you had no ties in the data, so you had 694 subjects all at a different value, you can detect the least impressive effect. But you see there's not much difference. Once you get about 7 categories, maybe 6, you have almost the same information as a continuous outcome, but that's only if the distribution is fairly uniform. So take a look at this blog article, and I think it will help you in understanding the power of various configurations of variables. How continuous are they, and how uniformly distributed they are. So that leads into this little discussion about information content. A binary outcome has 1 bit of information, and if you look at the field of information, theory of information, information's measured in terms of binary digits or bits. So a 1-bit variable is an all or nothing. There's no gray zone, there's no close calls, and they're often arbitrary. So that is the lowest information that you can have in a variable, other than a variable that's always 0. So if no one had the event in your study, that's even worse. But this is the next worst possible situation. Now, systolic blood pressure has about 5 bits of information if you measure it to the nearest 4 millimeters of mercury. So it has a range of roughly 50 to 250, and if you were to write these numbers in binary digits, that's 7 bits. It takes 7 binary 0 1s to represent this sort of range. But if it's accurate to the nearest 4, that takes away 2 bits of information. So systolic blood pressure has 5 bits of information, and that's a direct reason why a study of blood pressure is going to be crazy to classify people as hypertensive or not. The power is going to be way bigger to use the actual blood pressure to get that at least 5 bits of information. Now, for a binary event, if the proportion of subjects having the event is small, the time to a binary event has roughly the same information as just a yes/no variable. So we like to use time to the event, but it's not always making it act like a fully continuous variable. If your proportion of events is much greater than a half, then the time to event is now acting like a regular continuous variable like blood pressure, giving you a lot of power. If you look at cardiovascular studies, a lot of these studies are 6 to 10,000 patients in sample size, and that's a direct result of using a low information binary outcome. Now, dichotomization is one of our biggest enemies, and it's really hurts your statistical power, and your power is hurt the least if you dichotomized at the unknown population median, and even then your power is greatly reduced. You might need 40% more subjects randomized, for example. But if you cut it at 2 standard deviations from the population median, the loss of power can be massive. In other words, you might have to multiply your sample size by a factor of 4. So in Chapter 18, we'll get into that in some detail. And then there's the infamous responder analysis, and there is a topic on datamethods.org that goes into detail about that. I would encourage you to look at it. Dichotomization is actually an ethical problem because patients enroll in clinical trials with the expectation that good science is going to be done, and that they're actually going to be fully used in the final analysis. And dichotomizing the outcome is like only using part of the patient in the analysis, and the sample size has to be greatly increased. So you have to expose an unnecessarily large number of subjects to the experimental arm. If you try to dumb down a variable to make it more clinically interpretable, that's a mistake, and I think it just substitutes one problem for another. So I hear a lot of clinicians say, well, we weren't satisfied to just tell you that the mean reduction in blood pressure with treatment B was 7 millimeters of mercury with some compatibility interval here, and we wanted to set a target of a 10 millimeter reduction, and in treatment A we got 31% reduced that much, and in treatment B we have 41. But they don't really ask the question, is the difference between 0.31 and 0.41 clinically significant? So you're really changing one problem for another, and there's no information about reductions greater than 10 or reductions that were almost 10. And so I think it's actually more clinically relevant to think about the 7 than it is to think about the 0.31 and the 0.41. Change from baseline, we're going to go through that in detail in a later section. This has everything going against it, and it's really hurt by measurement error. It's greatly hurt by regression to the mean, and it assumes that you've collected a second post-qualification baseline if the variable is part of the inclusion criteria. So if you're including subjects because their blood pressure is high in a screening visit, you have to have another visit to measure the blood pressure pre-randomization, and that's just strictly because of regression to the mean. So you're assuming the variable is perfectly transformed so that the subtraction works, that the post value is linearly related to the pre-value and it has a slope of 1.0. You're assuming there's no floor or ceiling effects and that the y is interval scale. So those are the hidden assumptions in change scores, and you can see that those assumptions are going to be very seldom satisfied. So what is an appropriate analysis? Well, it'll be analysis of covariance. So you have your your response is your continuous measurement, let's say at 12 weeks. You've got beta 1 times your treatment effect, so that's the effect of the treatment in a parallel group, say randomized trial, and then you have the effect of the baseline measurement, Y0 for, say, blood pressure. And by fitting the model like this, you'll find that beta 2 is often more like 0.8 than it is like 1. So it would have to be 1 for a change score to actually work effectively. And the farther it is from 1, the less power you have on the change score. But the change score can be fundamentally misleading, and it's quoted out of context. It really can be more regression to the mean than anything. So we'll be discussing that in more detail in chapters 14 and 13, but I think it's a very important issue. And then we're going to close with just a brief section about what sort of data we should be analyzing. Really, there is a lot of pre-processing that goes on, and we see this in proteomics with mass spectrometry. We see this with genomics, but we also see it in mice experiments, and there are some practices done in animal experiments that are truly horrifying from a statistical standpoint. So one of those is you have a control group of mice, and you get like a geometric mean of their response, and you divide that into the response of the experimental group. So experimental group could be like knockout mice or something. And so by taking the control group and dividing it in and treating these ratios as if they're raw data is a form of pre-processing that is incredibly problematic. So you're assuming there's no biologic variability or measurement error in the control animals. You're assuming that division or subtraction is actually okay for that type of measurement. You're forgetting that you're inducing a correlation between animals when they used to be uncorrelated. And so this kind of pre-processing is something to really be avoided at all costs. The control animals need to appear in the analysis as raw data. And just in general, whenever you're given a set of data, you want to have access to the rawest form of the data, unless your computer just will not handle that, some massive data set, and you're working with someone in bioinformatics that really knows how to properly normalize, and they've checked that there's no artifacts in doing that. You might need to normalize, but we really want to start with the raw data, if at all possible. So there are a lot of questions that have been posed, and I think some really great questions. And I'm just going to mention a couple of them. Some people are asking for good references for experimental design, and I'll add that either in the notes or in the webpage for the course. There's some great books for experimental design. And somebody mentioned the Montgomery text, which is a really good one, and there's two newer ones that I'll recommend. And somebody asked about splines. That's something we'll talk about much later. And I have a whole course that covers that sort of thing in detailed course notes that go along with my book, Regression Modeling Strategies. So what I'll encourage you to keep asking questions, and we'll see, the moderators will see if there's other questions at the end of the chat that we can address in the data methods topic for this particular session. But I would urge you to look at datamethods.org for this section that's in the link on the web page, and add more discussion and questions. We have another question is, would these recommendations, say not dichotomizing ordinal Y, apply to explanatory variables too? The answer is very much yes. So dichotomization does the most damage for the response variable, but it can do a lot of damage, almost as much, for the explanatory variables. And so when you dichotomize an explanatory variable, you are now obligated to measure a new explanatory variable to add to the model to make up for the loss of information from dichotomizing the one. So that's very important. Somebody asked, what if you want to estimate the association of one level compared to a reference? So that's something you do a lot with categorical variables, and you can do it easily with continuous variables to create, like, what is an odds ratio if you compare a 60-year-old with a 30-year-old. So those are very standard things to do. So keep the good questions coming, and I will see you a week from today at the same starting time. And if you have general suggestions about how the course is run, please put those on the general topic for data methods. So thanks so much for participating, and I will see you soon.